Today, I'm going to be introducing a kind of mini project that will allow you to use your creativity while also controlling more complex circuits than we've been working with previously. Previously, we've been generally focused on a single component we're controlling, like an LED, for example. But in this circuit we're going to be working with, there are several components we're controlling all at once. So let's take a look at that now. So the project you'll be working on is a light show that's going to be using basic LEDs, same as we've looked at in the session 0 and 1. And this time you're going to be working with a total of 9 LEDs at the same time. And your program will need to turn them on and off in a pattern of your choice. So this is kind of an open-ended thing. I've already prepared a schematic for the circuit that connects these LEDs to the Arduino. And the schematic will be provided for you in either the slideshow, or you can also find it on the GitHub repository for this workshop. And basically, I'm having everyone use the same circuit for one reason, is so that everyone's got the same level of complexity they're working with. And the second reason is that you'll be able to submit your code to me either through the sign-in sheet or by email, and if you choose to do that. And then I actually have the identical circuit set up in using actual hardware, and so I can record your light show running on it and then play that in a future session of these workshops, in order to, in case you don't have the equipment to make this light show yourself in hardware, you can kind of get the same experience this way. So yeah, I'll give more details for how that will go down later. So now let's look at the circuit schematic. So you can see there's 3 main parts here. First, you've got the Arduino board on the left, which is this rectangle with a bunch of pins sticking out of it. And then you've got the resistors, which are used to limit current, and there's one on each of these wires coming out of the Arduino board. And finally, you've got your LEDs. So let's start with the digital pins on the board. So pins 2 through 10 are all in use, and each one controls a single LED. As you probably expected, you will be using digital write to interact with the LEDs through the pins. Each digital pin connects to a 330 ohm resistor. So in terms of the color code for a resistor, that would be orange, orange, brown, and then gold for the tolerance. So the text on each wire that comes after the LEDs is telling you which LED in the 3x3 grid is connected to that wire, and you can use that to determine which digital pin is controlling it. So for example, the top wire connects to the top right LED, which is right here. So speaking of the LEDs, each LED is represented by this triangular symbol, and that the symbol, it indicates the direction that current will be flowing through the LED. And since the LEDs are arranged in a 3x3 grid, I've labeled each row. So you have top, middle, and bottom row, as well as each column. You have left, center, and right column. So you can use these for the row and the column to identify each LED. And since the symbols are pointing in the direction that current is traveling, you can see that the current will be traveling out of the board pins through the resistors and then down and to the right through these LEDs. And after that, the outputs of all the LEDs, in this case, it would be the cathode acting as the output, since current flows from anode to cathode. The cathodes all get connected into the same wire, which goes back to one of the ground pins on the Arduino board, which is denoted with this triangle symbol. So that way a single wire can carry the current back to the Arduino board, since in a physical circuit, you wouldn't be able to stick 9 wires into one of the Arduino's pins. So in a physical circuit, we'd be using a breadboard to connect the outputs of all of these LEDs together. And I would highly recommend using a breadboard in Tinkercad to help keep your circuit organized. Now, when you're replicating this circuit in Tinkercad, pay close attention to which digital pin connects to which LED. You'll definitely want to make sure that these connections are correct, because if you find an error while testing your code, you could have a hard time identifying if it's actually an error in your wiring or if it's just a bug in your code, which you don't want to end up spending a really long time searching through your code just to realize that it was a problem with your wiring. And assuming that you wire the circuit correctly, there is a chart in the slides here that lets you quickly check which pin number corresponds to which LED. And so you'll use that pin number in the function digital write to control that LED. So now that we've covered the schematic, are there any questions about interpreting the schematic or how the circuit works in general? Okay, looks like everyone is understanding. So there's something, actually a trick I can show you to make it even easier for you to keep track of which LED you're controlling when you're using digital write. So I'm going to show you an example, the example code for a light show controller, which you can find this in the GitHub repository. So if you look at the very top of the code, I have these lines, there are 9 lines, which each begin with a £sign and the word define. Now, these are called preprocessor directives, which it sounds complicated, but they serve a very simple purpose here. So after the word define, there's a keyword, such as tr_pin, and then followed by a number. So this preprocessor directive is simply creating an alias for this number, which in general, it doesn't have to be a number that you use. You could also create an alias for for entire pieces of code. So in this case, where we want an alias for the numbers which correspond to pins on the Arduino board that are controlling our LEDs. So this means that wherever I write one of these keywords in the code that follows these defined statements, it will be replaced by the associated number during the compilation process. So anywhere where we want to specify a value, we can write the keyword instead, so that we can easily read the code without having to look up which pin number corresponds to an LED. Because here, for example, TR pin, it's kind of intuitive that is referring to the top right LED in the grid. So we know when I say digital write and the first argument is TR_pin, then I'm changing the state of the top right LED. So let me check if there's any question in the chat. Okay, now that we've covered that, let's talk about the timing aspect of the light show, because that's going to be very prevalent in your code here. When we're controlling a light show, we don't want all the commands to be executed as soon as possible, because the microcontroller's processor is executing instructions much faster than we can perceive. So we need the LEDs to remain in a certain state long enough for us to notice notice the LED turning on before moving on to the next state. So when we want the Arduino to hold off on executing more commands while maintaining its current output, we use the delay function. So if you've seen session 1, then you already saw this in action when Sahas used delays to hold an LED at a certain brightness level for a certain amount of time. And when we're using the delay function, basically we're going to be varying the length of time we delay for, depending on how we want the pattern to play out. So calling delay and passing a number as the only argument will cause the Arduino to pause for that number of milliseconds, and thus you can precisely control the length of time for which an LED stays on. So yeah, and the main thing to keep in mind here is that we're counting in milliseconds when we decide which number to pass as the argument for delay. So if you want to delay for 1 second, we just have to use 1000. So to help you understand, I'll show you an example so that you can see the delay function in action. I'm gonna be doing this in Tinkercad. So in this circuit, we're just controlling a single LED, and so the code is pretty small. And so we do, in the setup function, we're just doing some general stuff like setting the mode for the digital pin, and then starting the serial monitor, which we learned about in session 1. But we've also got this integer variable delay val, and we're initializing it to 1000. Delay val is giving a number of milliseconds, so the 1000 means 1 second. That's because we're using it as the argument for the delay function. And what happens in the loop function is the LED will be flashing on and off, and the interval for which it stays on or off is given by delay val, because we add a delay in between each time we change the state of the LED. So then after we've flashed the LED on and off once, we check if there's that number on the serial monitor, and then if there is, we will update delay val with numbers, so while the program is running, you're able to change the rate at which the LED is flashing. So let's take a look at how it works and also what happens when we change the value of delay val. So when I first started, you remember delay val was set to 1000. So with a delay of 1 second, that means each time the simulator ticks, the simulator time ticks by 1 second, the LED is going to change states. And also have the current value of delay val printing to the serial monitor. Now, what do you think is going to happen if I put in the number 500 into the serial monitor? Are there any guesses? Well, let's take a look and see what happens. So there's a slight pause while the simulation is processing. Then now you can see the LED is flashing much faster. To be exact, it's flashing at twice the rate that it was before, because by going from a delay of 1000 to a delay of 500, we are basically doubling the number of times the LED changes state each second. So that's why it's flashing faster now. We can also go in the opposite direction. If we put in 2000, that is twice the amount of delay that we had before, and the LED is going to be flashing slow at a slower rate. So hopefully that makes sense, and now you have a good understanding of how the delay function works. So now we can discuss how we would use the delay function. So I've got a question: why is it called the serial monitor? The reason why is because it's used for serial communication with the Arduino board, which that just means you're sending data at what it would be. Usually it's between 1 and 8 bits at one time. And so basically is what a sender and a receiver, and you're sending these bits by controlling data lines. But I'm probably getting too much into it, and there's already information about the serial monitor and how it works in session 1. So if you want to learn more, you can just watch the recording for session 1. So back to the subject at hand, we're going to see how we can use the delay function to create correct timing in a light show. So if you're going to have LEDs flashing at different frequencies in your design, you'll need to make sure that you use delays that are no larger than the shortest period of any of the LEDs flashing. And that's to make sure that your delays do not prevent any of your LEDs from flashing at the correct time. So as an example, let's say you wanted to flash LED 1 by toggling its state every second, and then you wanted to flash LED 2 slower by toggling its state every 2 seconds. So the two LEDs would have different amounts of delay you need to wait between executing the code to change their state. And as you can see in this diagram, the signal applied to LED 1, we're showing it on the top. The signal applied to LED 2 is shown on the bottom. Now, these are digital signals, which means they're either high, 5 volts, or low. When they're in line with the dashed line, they're high. When they go back down, they're low. So if we analyze the diagram, we can see that the signals are forming square waves, and the period of the top wave is 2000 milliseconds or 2 seconds, and the period of the lower wave for LED 2 is 4000 milliseconds or 4 seconds. So to generate these waves with the Arduino board, we need to delay by either 1000 milliseconds or 2000 milliseconds between toggling the LED state, depending on which signal we're talking about. But if you look at the top here, you'll notice that delaying by 1000 milliseconds twice is equivalent to delaying by 2000 milliseconds, because you can safely assume that if you're doing something as simple as toggling an LED in between your delays, that's going to take up almost no time at all relative to the amount of time you're waiting. So you can say it's still 2000 milliseconds approximately. I've got, okay, that's it. So in basically what you could do is delay by 1000 milliseconds each time over and over again, and we would toggle LED 1 after each delay, but we would toggle LED 2 after every other delay, so we still get that full 2 seconds where LED 2 is high, even though we were doing 2 delays in that time. So in an actual light show, you could have many more than 2 LEDs flashing with many different periods, but as long as all of the periods have a common factor, in this case that is 1 second, you can simply delay by that common factor each time and have each LED wait until enough delays has been done for the total time interval you need to wait to have passed. And in order to do that, you'll need to keep track of how much time has elapsed in total. So you'd usually do that using a variable that increments after each delay. So now, another topic we looked at in session 1 was state machines. So basically, you can think of a light show as a state machine that runs on its own without input from a user. The main variable used to determine the next state in this case would be the time elapsed, although other variables may be needed to control the order of states. And note that in this case, the time denotes the time elapsed since a state was entered, not the total time since the state machine was started. So in this picture, there are 3 states representing 3 possible configurations for the LEDs, of which there are 4 in this case, numbered 0 through 3. The first configuration has all LEDs off, and the next configuration has only the odd numbered LEDs on. And finally, the third configuration at the bottom here has only the even numbered LEDs on, which are 0 and 2. So let's assume that we're starting in the state with all of the LEDs off. So after 1000 milliseconds, we will be changing states because the arrow looping back to the off state, which tells you to remain in that state while this statement is true, time less than 1000. That's going to effectively mean you wait for 1 second, and then you will need to take one of these other 2 arrows. And so which arrow we take depends on whether an internal variable called next state is set to even or odd. And this could be a Boolean value with a false value indicating odd and a true value indicating even. If the next state is set to odd, then we will transition to the state where only the odd LEDs are on and reset the timer count to 0, since we need the timer count to measure the time elapsed since the state was entered. So we're going to be resetting it every time we change states. Now, in this new state, we need to wait 2000 milliseconds before transitioning, because that's the number indicated up here above the looping back arrow. There's only one possible transition out of this state, that is back to the initial state. When transitioning back, we set the next state to even, as denoted by the text below the arrow. And now that we're back in the off state, we have to wait for 1000 milliseconds again. After that, the next transition we go to the state where the even LEDs are on. And then we're going to wait 2000 milliseconds in that state before transitioning back, and in the process setting next state to odd, so that after you've finished that transition, you're back where you started and the cycle can repeat. So, while this is a highly simplified example, it can be extended to the light show controller to allow for complex sequences to be created without needing to make one really long chunk of code, since you're just executing the same code over and over again and using logic to set the state variables. And if you've taken the E or CS 120 series, then you're aware of the kind of complex behavior that a state machine can produce. And however, you might be wondering how all this translates into code for the Arduino. And so I'll show you the code which implements this state machine. So here I have a corresponding circuit in Tinkercad. So we have 4 LEDs, again numbered 0 through 3. And these are connected to digital pins 2 through 5. You'll notice that as with the schematic for the light show circuit, we've got it's hard to like remember which pin each LED will connect to, since the LED number doesn't even match with the corresponding pin number. So what we do to help with that is add a function which will map the LED number to the pin number which controls it. And in this case, we just need to take the number 5 and subtract the LED number from it. For example, LED 3 corresponds to pin 2, and 5 minus 3 equals 2. So that we'll be using that so that we can refer to the LEDs by their number in the code. Also, now for the state machine itself, we've got the first thing we need to do is make this enumeration, or enum for short, which is just a variable where we've defined the 3 values that it can take, and these 3 values represent the 3 states in the state machine. So this can be used to store the current state of the state machine, and then we've got 2 other state variables here. The first one is next state, like we saw in the diagram. It's a Boolean variable, and we're defining 0 to represent odd and 1 to represent even. So if next state is 0, that means we'll be transitioning out of the off state and into the odd state. And finally, we have the timer variable holding the time elapsed since entering a state. In this case, we're counting in seconds, so since the common factor for the delays in the states is 1 second. Since either 1 second or 2 seconds, we can always count by 1 second. So our delay will use, if you look down here, our delay will use 1000, and then we'll be incrementing the timer variable so that counts the number of seconds. Now, in the setup function, it's still pretty standard. You're just setting the pin modes and then initializing our state variables. So like I gave in the example when we were walking through the state machine, that our initial state will be off. The value next state will start as odd or 0, and the timer needs to start at 0. And in the loop function, we have this programming construct called the switch statement, and this switch statement is frequently used for state machines when you need to execute a different set of code depending on the value of a variable, and that variable, it's not a Boolean, so it's not binary, but there is a like fixed number of cases for what its value can be. In that case, you could use a switch statement in order to control your program. So inside the switch statement, are going to be listing cases like this, where you specify values that the variable could take. In this case, since we're using an enumeration, we've defined exactly which values it's able to take, and we can just create a case for each one of those values right here. So there's a case for off, a case for odd, and a case for even. There's also a default case, which is what would be used if none of the other cases are met, but that shouldn't be possible in our code since state can only take on 3 variables, and we've got a case for each one of them. So I'm really just leaving it in here for the sake of explanation. Anyways, the code inside each of these cases is determining the behavior of your state machine. So for the off case, the first thing we do is turn all the LEDs off just by using a for loop over the 4 LED numbers. After that, we are checking if the time elapsed is at least 1 second, and if it is, then we know we need to transition to the next state, and that's going to be dependent on the value of the next state variable, which, as we discussed, is going to be 0 or false for if odd is the next state, and 1 or true if even is the next state. So since the value we need to assign to state is dependent on one Boolean value, we can use this fancy syntax to write this statement all in one line instead of using an if-else statement, which would work just as well if you wanted to use it. So how it's going to work is if the value of next state is true, or in general, whatever comes before this question mark is true, then effectively this entire statement would be replaced by whatever is between the question mark and the colon. So that would be the value even. So state would be assigned to even. However, if this were to evaluate false, then the whole statement would be replaced by odd instead. So whatever comes after this colon. And so that would be the same as having an if else dependent upon the value of next state, and after the if you would put state equals even, after the else you would put state equals odd. This is just a way of doing that same thing in a much shorter way. And then of course we're going to reset the time before we enter our new state. And at the end of each case, you have to include this break statement. Then we move on to our next case, which is for the odd state. So in this case, we're turning on the 2 LEDs that are odd. However, we don't need to worry about the LEDs which are even, because since we're always going to be in the off state before we're in the odd state, we already know those LEDs are going to be off, which we want them to stay off, so we don't have to give them a new signal. Then we have the logic for transitioning states. In this case, we don't need to think about what the value of next state is. However, because we're always going to be transitioning to off from this state, however, we do need to change the value of next state to 1 which represents even, so that the next time we transition out of the off state, we will be going to the even state, and thus we will alternate between flashing odd LEDs on and even LEDs on. And then the logic for the even state is basically the same, just changing a few values around. And that's all you need to have for this state machine. And admittedly, it may seem like we're putting in way too much effort for something that just flashes two sets of LEDs off in an alternating pattern. But when you've got a lot more LEDs to work with, then in some cases it will be a lot more efficient to just use a state machine like this. It certainly helps you visualize what it's going to be doing, because you can make a state diagram like in the slides here, and then that'll allow you to visualize what you want your circuit to do before you actually program it. So let me just verify that the code works by showing you the simulation. So yeah, you can see it's functioning as intended. Okay, are there any questions about that?
No, I'm good.
All right. So now I've got some final tips to use when coding the light show controller. So first, make sure that you remember to set your pins as outputs using the pin mode function when you're in this setup function for your code. And since the pin numbers are all integers between 2 and 10, you can actually do this using a for loop. So, for example, I do it right here in the example code. So the index is going to start at 2. It's going to increment all the way up to and including 10. And each time we're going to call pin mode with the index value as the pin, so that we're going to cover all pins 2 through 10. And additionally, I would recommend using Boolean variables to determine the state that your LED is set to when you call digital write, rather than just using the high or low values like we did in session 0. And because that allows you to, first of all, it's really important when if you're gonna be using a state machine, because then you have a variable that can change at different points in the state machine, and that will allow it to affect how the light show looks. And it doesn't necessarily have to be a state machine, though. Like in this example, what it's doing is just turning the LED, all the LEDs either on or off in a specific sequence. And each execution of the loop function, it will change the state of all the LEDs, and then it takes the logical inverse of the variable that's controlling the state. So that way, whatever state it's setting the LEDs to on the next execution is going to be the opposite of what they were just set to. And so you get an alternating pattern. Now, if just alternating LEDs between on and off seems boring to you, you can also use PWM as discussed in session 1 to vary the brightness of each LED, which could make for more interesting looking light shows. However, be aware that the brightness the LED shows in Tinkercad may not accurately reflect how bright the physical LED will be. So if you're going to be submitting your code and it uses PWM, then the footage of your light show may not match how it looked on Tinkercad. So, like I said at the very beginning, you'll have the opportunity to submit your code to us so that we can record footage of your light show in action on an actual circuit. This footage will then be presented during the introduction to future sessions of this workshop series. In order to give us your code, which we will then upload into a physical Arduino board, you can either submit a file containing the code or submit a link to a Tinkercad project or GitHub repository that contains the code, as long as you've made that publicly visible beforehand so that we can actually access the code. If you are submitting a link, you can do it through the sign-in sheet for this session, and that is probably the preferred method for us. However, if you are submitting a file or you cannot use the sign-in sheet, then you can email me at jcarl023@ucr.edu with your submission, and then I'll attempt to notify you if I can't get your code to work for some reason, like there's some error which you would need to resolve before it can work. And if you need to resubmit, then you can simply email me your new submission, and hopefully I'll have time to take another look at it and then get it recorded. So if there are no questions about this process, then in the remaining time for this session, I'll show you some of the features that Tinkercad provides for sharing and managing your circuits, since that will be relevant to the current project. So the first thing I want to explain is how to download your code into a format where you can put it inside of the Arduino IDE. Like that, you could simply copy paste your code if you've got it in Tinkercad and put it into the Arduino IDE that way, and then you could save it as a Arduino sketch, and that'll probably work fine. However, I want to show you that how Tinkercad lets you download your code, just in case you want to do it that way. So basically, if you're in the Tinkercad workspace and you've already gotten one or more Arduinos out and they have some code already written in them, then when you have the if you have this code panel out, at the top of it, there's this download code button. If you then click that, for each Arduino with code in it, it'll give you a separate file. These files are using the .ino extension, which is the extension for a Arduino sketch, which means it will automatically be recognized by the Arduino IDE. The name for these files is going to be somewhat similar to the name of your Tinkercad project. However, characters like spaces will be removed because you can't have those in the name for an Arduino sketch. Now, if I try to open one of these in the Arduino IDE, first, before it'll let me use it in the IDE, it'll actually have you create a sketch folder to basically store this file in, because the IDE needs your sketches to be organized into separate folders. So it'll create the folder when you press OK, and then you'll see your code show up on the IDE. Yeah, so from here you could upload your code to a physical Arduino board. So if we go back to Tinkercad, there's some other features I want to show you. First of all, there are many circuits in Tinkercad which have already been made by the community, and at times you may want to check out the code that a circuit uses, or to see how it works, or to modify it yourself. And this is very easy to do in Tinkercad, since anytime you click on a publicly visible circuit made by someone else, and you can find a lot of them in the gallery, then you'll be given the option to copy and tinker, which will effectively clone the design into a new circuit which you have control over. For example, let's just use this circuit here. So actually, you don't even need to copy and tinker in order to see the circuit in action or look at the code. You can just press this simulate button. And then it'll be as if you're in the actual workspace. You can run the simulation, see how it works. You can also look at the code. However, what you can't do is make any changes to the code. So if you want to try making changes to it, you'll have to click copy and tinker, which will open up a copy of the circuit that is actually yours, so it's in your collection of circuits. And then you'll be able to do all the same stuff with it, and you can type text. So this way, this makes it really easy to learn how different parts work, is by finding a existing circuit and then messing with the code to see what the changes do. And by the way, I'm planning on, after letting you work on the light show project for about half a week, so until the end of this Saturday, you'll basically have that time to try making the circuit that is represented by the schematic from the slides by yourself on Tinkercad. And after that point, I'll actually release a sample circuit that you'd be able to use instead of one that you made, just in case you weren't able to get the wiring part done. You'll still be able to do the coding part. And the link to the example circuit will be released on the GitHub repository inside of the session 2 folder. I'll show you specifically where that is. This is the repository for the workshop. There is a folder for each session. In session 2, we have the demo code, which is just the code that we went over during the workshop session. Then we've also got the Light Show project folder, and this gives a brief overview of the project, and other important materials will be put here. So when I release the link to that Tinkercad circuit, I'll be putting it in here, probably in this README document. So now there's a few more things I want to show you. And I know it's reaching 6 o'clock, so I'll make this fast. So if you're in your own collection of circuits, like if you go to you can always go to your dashboard by clicking on the Tinkercad symbol in the top left corner, and then you just have to choose circuits. If you hover over one of your circuits, you will get this gear that appears. If you click it, this drop-down list will appear and give you some options to manage your circuits. First, let's look at the properties. You can edit things like the name of the circuit, just give it a description that will show up for other users if you choose to make your circuit open to the public. And the main thing here is the privacy options. So you can choose to make your circuit as a totally private, where only you can see it, or totally public, where anybody can look at it or even make a copy of it using the copy and tinker. And so if you want to submit your light show using a link to a Tinkercad project, you'll have to make it public this way first. So for now, I'm going to leave this circuit private. Two other options in this drop-down menu that I want to mention are the option to duplicate a circuit. This is essentially the same thing as using copy and tinker, except you're doing it to your own circuit. So you're going to get basically an identical replica. And then finally, you can delete your circuit, which will just remove it from your collection. So those are all the extra features of Tinkercad that you may end up using during this workshop. And that actually brings us to the end of our session 2. I've got some extra announcements to make. So I've posted the sample solutions for the serial monitor exercises from session 1 to the workshop GitHub repository. And then I've also created a document compiling all the useful links we've shown on the slide so far. And I've added it to the Google Drive folder where the workshop slides and the syllabus are found. So hopefully this information is useful to newcomers, as well as those of you who have been following the workshop since the first session. So thanks for coming. and good luck on your projects.